Once again, I want to welcome you all to this. Now, the difference between what we're about to do and what we did the previous time is that this is a biennial Malmquist, but there is an extension of it. Okay. So I want to quickly remind you of some few things. First thing, what is an index and what is the Malmquist productivity index? What is an index? An index is a tool that compares relative performance. So we have consumer price index, producer price index. In the past, we have had the Laspey's, the Pache, the Fisher, the Tombist, and then the Malmquist productivity index. Okay, now the Malmquist was introduced into the literature by Caves, Christensen, and Dywett. In 1982, they introduced the Malmquist. Please note, in 1982, even though they introduced the Malmquist index, they had not been using a non-parametric data envelopment analysis for it. So they've introduced it, and you will later know that the one who brought the DEA to estimate the Malmquist non-parametrically was the one by Fair, Groskov, Lindgren, and Roos, and later on Fair, Groskov, Norris, and Zahn. Okay. It was named when Christensen, Caves, Christensen, and Dywett, when CCD actually brought it in 1982, they named it after Malmquist, Professor Sten Malmquist, because of the great work the man has done in index numbers and quantity theories. So the Malmquist is basically a bilateral index. Bilateral means it's looking at two, situations. We call it adjacent index, okay, where you are assessing productivity change over 2 time periods, sometimes even across 2 different economies. There are 2 versions of the Malmquist, the DEA-based Malmquist. One is the adjacent, which is by Fair, Groskov, Lindgren, and Roos, and the Fair, Groskov, Norris, and Zahn in 94. Then you have the base period by the good friends of Berg, Fossand, and Johnson. Okay. They look at the base period. Now the base period will have a single technology, but then the adjacent will have, estimating the performance relative to two different technology. And then you move to the subsequent period and then you deal with it. And then you look to the subsequent periods and you deal with it. But at adjacent, the base period, that one will focus on a single technology. So you can have maybe the year 2000 as the base period. Everybody is being measured relative to that base period. Okay. And on the basis of that, it will handle the problem of circularity or the transitivity. Okay. Why is the Malmquist so popular? Well, compared to the other indices, it uses distance functions. Okay, so it makes it popular. It also allows you to decompose productivity into several components. And it's also good to do that because once you have several components, you will know the sources of the decomposition. You can see that Dyna is now developing a model, an 8-factor decomposition, okay, to know several sources of the model. But the Malmquist index is not the only index that is used to measure productivity. We have the Hicks-Mustin index, okay, sometimes kind of wrongly referred to as total factor productivity index. And then we have the Leuenberger indicator. That one is basically from the directional distance function. Okay, and we use that to be able to measure productivity as well. That one deals a lot with negative data, and you can increase output and decrease input at the same time. There are different graphs on the orientations for the Malmquist, and you got to know which one. What I have done is that most of you have made you know all of these graphs so that you can draw all of them. The capacity to draw all of them is important. Okay. So in a normal efficiency, you can have an output-oriented graph like this. Okay. You can have an input-oriented graph like that. Now the output-oriented graph is exhibiting concavity. So this whole output set or the output possibility set, you're projecting the firm onto the frontier. You're pouring it out. And then the input orientation, you are reducing the input. So you can have X2, X1, and you are reducing it towards the origin. It is the fact that they are towards the origin, that is why they are called radial measures. Then you can have a situation where you have input and output. So in this input and output graph, you are reducing the input when you are moving to the left from the DMU, and you are increasing the output when you are moving to the top from the DMU. Either way, you will hit the frontier somewhere. Now you can see that this frontier is smooth. So it is not really a real frontier. It is just an absolute frontier. Okay? Because the real one will have a piecewise linear envelopment. Piece, like the ones on the top that you see. So these are the different kinds of frontiers. Okay? And you're going to learn them, but some of them you've learned already. This is a CRS graph, which starts from the origin, portrait out. You will draw all of these. These are two different graphs. The first technology is technology related to time t, and then the technology related to time t plus 1. The VRS frontier, that one is piecewise, because VRS assumes that there are varieties of sizes. Okay? So you can have decreasing returns. One part will be having the decreasing returns, another corner point will be having constant returns, then you can have increasing returns and all of that. So as you are growing, as you are starting from the graph bottom here, you are exhibiting increasing returns. Then in the middle somewhere, you're exhibiting constant returns. Then towards the end, you're exhibiting decreasing returns. That's VRS. They are variability. They are variabilities. Your capacity to draw each one of these graphs is important. Your job is to create a hypothetical data set and then draw the graphs yourself. And that, ladies and gentlemen, is what I'm about to do. I'm going to do one of these graphs in a hypothetical framework. The data set is the one in yellow. Yellow. If at this stage you don't understand something, always let me know. The data set is in yellow. Now, if you can look at it, I have X1 and X2. And the fact that I have X1 and X2 different numbers, but Y has been normalized to 1. We have year 0. As you can see, the first 5 DMUs are in year 0. The next 5 DMUs are in year 1. Okay, so you can see all of that there. All right. So what I'm going to do is I'm going to continue by using the biennial graph. Okay, so as for the Malmquist, we have looked at it already. What I'm going to now do is to look at the biennial Malmquist. There are several extensions of the Malmquist. There's no doubt about that. The adjacent Malmquist that we looked at has been extended into the variable retention scale according to Ray and Desli decomposition in the American Economic Review. But Ray and Desli are not the only people who have extended the original Malmquist index. There is a base period index by Berg, Fossan, and Johnson. We said it the other time. The Malmquist has been extended into the global frontier shift by Asmad and Tam. The sequential Malmquist of Shestalova is there. Then we even have the sequential Malmquist-Leuenberger index. Okay, that one uses the directional distance function. That is there by O. The meta Malmquist is there. The overall Malmquist is there. The Pastor and Lavelle global Malmquist is there. The O global Malmquist-Leuenberger index is there. Tauhidi and his team have developed the global cost Malmquist. That is there. There is the global secular global profit Malmquist. That is also there. Then what we are going to study today is the biennial Malmquist of Pastor and Lavelle, Asmald and Lavelle. The biennial Malmquist we are going to consider today, Mohammadi and Yusuf Popo have also extended it to negative data. We will not look at that. The Malmquist has been extended into the cost Malmquist by Maniadakis and Tanasolis. And that has also been extended into meta frontier Malmquist. And so there are several other Malmquists that one needs to look at. Now, I have already gone through this Malmquist with you, but what I'm going to do today is the biennial. So what I'm just doing is giving you a mental jog, a recapitulation of the previous ones. So take notes that we have not started. I'm just warming you up. Just a second. I'm warming you up by looking at the previous ones. Okay, by looking at the previous ones that we know of. So the original Malmquist is this. The Malmquist is made up of 4 different efficiency scores. In this output-oriented efficiency score, it is output-oriented. That's why you see OO. It is output-oriented because I'm using phi here, phi here. You can see that these are the 4 different efficiency scores. That's a Malmquist. Fair, Groskop, Lengren, and Roos decompose it into 2. That is what you see here. The efficiency change, the technical change. They are all in output-oriented. Then, Fair, Groskop, Norris, and Zahn decompose it into 3. Pure efficiency change, scale efficiency change, then technical change. We've done these already in the previous slides and videos. Okay, now, Ray and Desli criticized the decomposition of Fair, Groskop, Norris, and Zahn. And then, because when you look at it here, when you look at it, you can see that these people are, if you look at the technical change, they are talking about decomposing the thing relative to one particular frontier. Now, the frontier here is the constant returns to scale frontier, as you can see here. The constant returns to scale. The constant returns to scale frontier. C, subscript C means constant returns. Subscript V means variable. So they criticize it for not estimating these things relative to both variable and constant. So Ray and Desli decomposition, when you look at it, first look at this, look at the scale, okay, and then the pure technical. First, look at the pure technical. Look at the technical change here. The technical change of Fair, Groskop, and Lavelle, you can see that the subscripts are all C, 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 which means all of them were estimated relative to what? A constant returns to scale technology set or frontier. But then they were claiming that they were doing variable returns to scale. And variable returns to scale means that you need to estimate the thing relative to a VRS frontier and not a constant returns to scale frontier. That is why Ray and Desli comes and then critique them. And so if you look at the Ray and Desli decomposition, the PTC, that is a pure technical change, you will notice that the PTC here, the PTC here, it has something. It has the V instead of the C. So all of them are estimated relative to a BRS frontier instead of a CRS frontier. So note that. And then of course, they spoke about a scale change factor. Okay, we've looked at all of this the previous time. Now, Wheelock and Wilson also comes and introduce a 4-factor decomposition. Now, what is the difference between the Wheelock and Wilson decomposition and the Ray and Desli decomposition? Guys, please wait. Okay, and just monitor something very quickly. The difference has to do with the fact that the scale change for the Ray and Desli, that scale change was split by Wheelock and Wilson into scale efficiency change, okay, and then scale technology change. Okay, so that's what they did. They have split the scale change of Ray and Desli into scale efficiency change and scale technological change. So it means that when you multiply the scale efficiency change by the scale technological change, you get back the scale change of Ray and Deli. Now, when you check their pure efficiency change, they are the same. Pure efficiency change, they are the same thing. When you check their pure technological change, they are the same. When you check their pure technological change, they are the same. The only difference is that the scale change factor for Ray and Desli is a product of the SEC and the STC of the Wheelock and Wilson. When you are able to get these distinguishing features, it helps you to know. Now let's move on. These are basics. On the basis of that, let's go to the biennial, the focus of today. The Biennial Malmquist itself was introduced by Pastor, Asmald, and Lavelle. In 2011, it has three good sides, beautiful sides. Linear programming infeasibilities, which normally appears whenever you are calculating the mixed period infeasibilities under the VRS, is avoided under the biennial. We shall prove that. 2, when you compare it with a sequential Malmquist, which does not allow you to compute technical regress, this one allows you to compute technical regress. 3, the global Malmquist also solves the infeasibility problem and also computes the technical regress. But then with the global Malmquist, and of course the global Malmquist is also secular and transitive. Okay? The issue with the global Malmquist is that it doesn't allow you to recalculate the productivity when a new time period is added to the data set. So the moment you add a new, let's say you calculate productivity for year 2000 to 2005, and then you get a new data set, which is 2006. Once you add that 2006 to, you got to recalculate the entire data set because it's possible that that new data set can influence the entire results. But then the biennial we're about to look does not need to be recomputed when a new data set is added because the previous ones that have been computed were computed in an adjacent 2 years. So you're looking at 2 adjacent years. But then the global, it compiles all the years from all the data set together and create a single global technology or a meta frontier, and then estimate everybody relative to the meta frontier. So the likelihood of you affecting the results, even if you have a new data set brought in, will be affected. I will demonstrate all of this in the process. So that is why the Biennial Malmquist is good. So the Biennial Malmquist, you create a biennial benchmark. And that benchmark is defined as the convex combination of 2. The word 2 is important. Not all, but 2. But if it had been the global, it would have been all. Of 2 adjacent time periods. So there are 2 adjacent time periods whose frontiers may have intersected each other because of non-Higgs neutrality. And so because of the possibility that the frontiers have crossed each other, now some of them may suffer from infeasibility when you're calculating the cross-period efficiencies. So the underlying reference here for the biennial is based on the 2 adjacent time periods. But for the global frontier, the underlying reference technology for the global is that it uses all the data set from all the DMUs and all the periods, and then create the global frontier. So if somebody should ask you, what is the difference between the global frontier or the meta frontier in productivity and the biennial frontier? What would you say? This is where I ask you a question. What is the difference between the global frontier and the biennial frontier in productivity estimation here? What is the difference between the 2? Okay, you can unmute yourself and tell me or raise your hand, because I want to be sure that you know what you are doing. Dinah, what is the difference between the global frontier and the biennial frontier? What is the main difference between the 2? Eva, do you know?
So please, I'm thinking through.
Eva, do you know? Macleod.
No.
Eva, are you talking?
No, I'm not talking.
Selena, do you know? Okay, Morrison.
Okay, Doc, I want to try. So from what I heard, then it means that the global Malmquist productivity index, that one captures the biennial Malmquist productivity index.
That's perfect.
That one is subsumed in it.
Yeah, that's
So,
well remembered. That is so true. There's no question about that. Okay, I'm not going to use a piecewise linear, but I'm going to use something briefly to explain what I mean here. Guys, it's important to understand this, mate. You got to understand it. If you switch off at any point in time, you switched big time off, big things off. And when it comes to you doing it, I'll let you do it because I'll now use this thing as a way to indicate that I've taught you. If you have a frontier, and I'm not going to use piecewise for purposes of easiness, and you have this frontier, which is for time frontier t, and I have another frontier, which is frontier t plus 1. Okay. On the basis of this, I can create a new frontier from here, capturing this as the biennial. So this is the biennial frontier. Okay. I can have another frontier, okay, another frontier which is t plus 2. Okay. I can have t plus 2 like this. Okay, t plus 2. Okay. I can have another one like this, which is t plus 3. Now, if you look at between t plus 1 and t plus 3, okay? Now look at t plus 1 and t plus 3. I'm combining t plus 1 and t plus 3 into creating another biennial. Okay. So that's t plus 1, that's t plus 1, that's t plus 3. Okay, so I have created another biennial, which is between t plus 1 and t plus 3. So in this case, the biennial is being created just between 2 time periods. That's what we say adjacent period. Okay, 2 time period, 2 adjacent periods. Now, if I want to create the global frontier, I just have to take the extremist. And the extremist one that I can think of and take is this one, which is t plus 2, capturing it all the way up to here. Okay. So this is a global. This global encapsulates everybody. But you can see that the biennial, which is the blue and the green, they are only encapsulating 2 adjacent time periods. They're just encapsulating 2 adjacent time periods. So you can see that the biennial Malmquist is a subset of the global Malmquist. And one can think of a global biennial Malmquist, which again, it is just like a normal global Malmquist in that regard. So why do we need the biennial if the global cannot encapsulate it? Because one of the things about the biennial, of course, is that it helps you to analyze 2 adjacent periods. Okay, that's the key. And again, don't forget, we said that you don't have to recalculate the entire data set, the entire productivity scores when a new time period is added to the data. So you got to be able to master these because this is critical. This is critical. Diana, you say you didn't understand. I hope you understand now. This is critical.
Yes, Doc. Thank you.
Now, in the case of a panel data, I've already said that there are 2 time periods for the biennial. And so the biennial technology will be a pooled or a meta frontier, okay, for the 2. But if it is for the global will be a pooled or a meta frontier for all of the firms. So in the case where there are more than 2 time periods, okay, where the time periods are more than 2, then you have a series of, U minus 1, that is when the time periods are U. A series of U minus 1 overlapping biennial frontiers that exist for each pairwise comparison. I've said this already. Okay. And the fact that you can combine 2 time periods into 1 biennial also means that you can combine 3 time periods into one triennial. So you can have a triennial Malmquist where you are looking at year 1, year 2, year 3, and then creating a biennial for all 3 of them. Okay. You can have that. All right. Now, how do you estimate the biennial? Well, the first thing to note is that, and we are going to use the output-oriented version. The first thing to note is that the biennial Malmquist was originally developed for the variable returns to scale because it is the VRS frontier that suffers from the linear programming infeasibilities. Having said that, though, we are going to show the biennial Malmquist for the constant returns because the constant returns doesn't suffer from infeasibilities, but we are still going to give the biennial for that before we give the biennial for the VRS. Okay, so the benchmark CRS technology, T, and the best practice, you see the way I call them, the CRS technology is a benchmark technology. Then the VRS technology is a best practice technology. In year T and year T plus 1, okay? This is what they are. Now watch it carefully. You see the T subscript C. It is showing that we are dealing with constant returns in year T. So that is constant returns in year T. So the technology set is given by maximizing the phi with the intention of getting a constant returns to scale score, which is a member of real positive all terms. The M plus S is the entire matrix of input and output. And then you have the input constraint, and then you have the output constraint. The output constraint, you see that the phi is multiplying the Y. You have the VRS, the non-negativity constraint, which is a lambda J to the power T. And then the number of firms are J1 to N. This is a constant returns. No VRS technology, no intensity factor, no VRS constraint in this. Now look at the next one. The next one, you can see the VRS constraint here in blue. That is the addition. That is the only addition. And then you can see that this one, instead of using year T, I decided to just use year T plus 1, just to distinguish it. And you can see that in this year T, but it's a VRS. That's why you see a subscript to V. Okay. You are still maximizing the phi, which is an output-oriented efficiency score, which is part or a member of the real positive, real numbers. The input constraint is what you see here. The output constraint is what you see there with a phi multiplying the Y to indicate that it's an output-oriented graph or output-oriented measurement. Then you have the VRS constraint, the convexity, constraint, and then the non-negativity constraint finally shown. So this is how the technology is documented or is written. What if it was biennial? Well, if it was biennial, and I'm going to use the VRS because you can do the same thing for the CRS, all right, but I'm using VRS because for biennial, the VRS is much more sensible because that is the one that exhibits LP infeasibilities. So if you look at the biennial technologies, watch it, biennial technology, we are maximizing the phi, which, it is in the VRS technology set. You need to know this. This is critical. This is a member of the real numbers, given the fact that this is the input constraint. Now watch the input constraint. It is the lambdas are relative to the biennial B, biennials. Okay, so the technology set is a biennial technology. This part, let me use a different color to show you this because you see your capability to capture this once and for all is very important. This part here, this second part is the technology set. That's a technology set. And the technology set, you can see that it has a B to subscript. The B subscripts are indicating the fact that it is a biennial frontier that is creating the technology. And the same thing is with the output constraint. Okay. Of course, the phi multiplying the Y shows that we are dealing with an output orientation. This is a VRS constraint, the convexity constraint. And the fact that you have a B instead of T or T plus 1 shows that we have combined the T and the T plus 1 technology. That's what it means. We have combined. So B is a combination of T and then T plus 1. I'll be showing that very soon. Yeah. Okay. So that is it. And so the fact that you have the lambda to the power B shows that we are dealing with a VRS, biennial. The only difference between this, the T plus the technology with subscript T and superscript T with subscript C to superscript T, and the one with a V, and they are year T plus 1. The only difference is the fact that the second ones here includes a convexity. So these ones here, they make up the convexity constraint on the lambdas. And like I said before, the biennial technology set is a combination of the two VRS technology sets. Is the convexification of the two, technology sets. All right. At this stage, if you have a question, you can ask. If not, let's move on. So you got to understand what I've just done. I've just shown you mathematically. Okay, but mathematical show is not enough. We need to make graphical sense. Okay. So we're going to make the graphical sense, but before that, let's look at the formula. What is the Biennial Malmquist? Well, the Biennial Malmquist is not made up. You remember we said that the normal Malmquist index. Remember, the normal Malmquist index is made up of 4 different efficiency scores. Okay. Or if it is distance functions, it's made up of 4 different distance functions. That's what we know. That will make up the Malmquist, the MPI. But then the Biennial Malmquist, which is the BMI, it is made up of 2 different efficiency scores. Because remember, the 4, 2 of them have been combined to make 1B, and another 2 have been combined to make 1B. Now, I'm going to show you quickly the constant, but I'll be focusing a lot on the variable. The fact that you have a C here means that this one is the constant returns biennial. And the constant returns biennial is just estimating the efficiency of the firm in year T relative to the biennial frontier. That is a constant returns biennial frontier, divided by the efficiency of the same firm in year T plus 1 relative to the biennial frontier. Constant returns. Variable returns is just a matter of changing the C to V. So again, you are dealing with 2 different efficiency scores in this context. This is biennial, 2 instead of 4. Okay. Now, so calculating the biennial Malmquist is straightforward if you know the frontier you created. But watch something. You need to decompose this. Okay. You need to decompose this frontier into several parts. And so what I'm going to do, I'm going to focus on the decomposition at this stage. In talking about the decomposition, before I actually explain the decomposition, I want you to understand what is happening, what is really happening in the linear programming balance. Okay. So we are going to estimate the efficiency of a DMU in year T plus 1 relative to something, relative to the biennial frontier. Now, note this down, and this is very important. This is very important. This is very important. Note that the biennial frontier, okay, the biennial frontier is only used when you are calculating the mixed period efficiency scores or the cross period efficiency scores. Why? You can tell me why. The biennial frontier becomes only useful when you are estimating the mixed period or the cross period efficiency scores. Why? Okay, because I need you be sure that you know what I'm talking about. You can tell me, okay? Maclay. Okay, Maclay, go ahead.
Can I say that because of linear programming infeasibilities?
Good. Because of linear programming infeasibilities, where?
In the cross period
Estimations. Good, good, good. That's the point. Okay, because it is only when you are calculating the cross period or the mixed period efficiency scores that you will encounter LP infeasibilities. And so the biennial comes in to solve that LP. So at that point, you will now replace it. So all the own period efficiency scores, I'm not going to look at it. I'm not going to look at it. I'm going to focus more on the cross period efficiency scores. But that's where you encounter the LP problems, the linear programming infeasibility. So what does this mean? If you look at the first part here, it says that the efficiency, okay, so what you are seeing here is saying that the efficiency of a DMU in year T+1, okay, T+1, take note, this is a type, T+1, okay, relative to a biennial VRS, of course, biennial frontier, relative to a biennial. This is a distance function. That's why you see that I've taken the reciprocal. So that to the power 1 means that I'm dealing with a distance function. But if I'm dealing with efficiency scores, I'm not using the distance function. So this is equal to efficiency scores here. And you can see that there is no reciprocal. So this means that you're going to have, the way you formulate it is what I'm trying to do here to help you to learn the formulation. So you are estimating the efficiency of a firm in year 2 relative to the biennial VRS frontier. Okay. You are maximizing the phi to be able to reach the frontier, in this case, the biennial frontier. And so if there are possibilities of infeasibilities in any of the estimation, the biennial frontier has been used to capture the two frontiers. So some way, somehow, it will be enveloped. The frontier will be enveloping the DMU in there. And any number will be feasible. Now, because the left-hand side of the equation is what is representing the technology, you can see that the left-hand side of the equation will be having the B to indicate the biennial, because now the technology is a biennial technology. The fact that you have a phi here with a T+1, because remember, this was a T+1 relative to the biennial frontier. You can see that a phi is multiplying the Y to indicate that it's an output orientation. This one there is the convexity constraint, the VRS, which is also in the biennial framework. And finally, then the non-negativity constraint. This is a typo. This is a typo. It's supposed to be greater or equal to 0 for non-negativity. All right. So that is how you estimate individually. But of course, the software does it all for you. Okay. The R software will be doing all, but you need to know what the R software is doing so that you can appreciate it well. And in your thesis or paper, you got to bring these formulations, these mathematical write-ups to make the work, much more believable. Now, previously, in the old classical Malmquist, there were a lot of arguments that were advanced in the literature that anytime you are estimating the Malmquist, use the constant returns instead of the variable. And the arguments that were, churned during those times was that because the CRS frontier always guarantees the estimation. In other words, it solves the infeasibility problem. That was the argument. Okay. But now you can see that now we can use a VRS because see, if the technology is exhibiting VRS, according to Simmer and Wilson, 2002, their test, the non-parametric test of returns to scale. If you test and the technology is exhibiting VRS, you can go and force and use CRS. So now with the help of the biennial Malmquist, one can still able to estimate the VRS and solve the infeasibility problem, and then go ahead and then calculate the productivity estimation. Now, let's go to the decompositions. This time in the world of biennial. As smart and term, and Asmald, Pastor, Asmald, and Lavelle, they are 2011 paper. It does all of these things we are doing. Okay. The only place that we are extending, I'll come to that, is the further decomposition we are bringing here. So this is a constant returns to scale. A constant returns to scale biennial is just the decomposed element of the efficiency change, which of course the B is indicating that it's biennial, the C is indicating that it's a constant returns. Efficiency change and the technological change. Okay. Now remember that efficiency change will not be different from the normal Malmquist because those are estimated relative to the own period frontier. So those are own period efficiency estimates. But the technological change, if you look at the technological change, see the formula, you can see that some of the formulas have cross periods. Okay, some of the formulas have got cross periods. So if you look here, because it has a cross period, we use a biennial to estimate it. And if you look at the next one, because it has a cross period, we also use what? A biennial to estimate that. So when they have cross periods, we use biennial to estimate them there. All right, now let's go to the Ray and Desli decomposition. And again, the original paper, 2011 paper of biennial did this. The Ray and Desli, watch it. The Ray and Desli decomposition, this is what it is. And this is the one all of you are doing. All of you are doing this. So it's important you all know this. The Ray and Desli decomposition, the RD is indicating Ray and Desli. You are having the biennial VRS multiplying the scale factor, which again is in the biennial world. The biennial VRS itself is split into the efficiency change VRS and the technological change VRS, all in biennial world, then multiplied by the scale efficiency change or the scale factor. This is the scale factor of Ray and Desli. Now let's get the details. This efficiency change is going to be the same for the Fair, Groskop, Norris, and Zhang. The technological change will not be the same because remember, the technological change version was under the constant returns. That was the criticism Ray and Desli gave them and said it should have been variable returns. So you can see that it is in variable returns. They are all in V, 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 V. Okay. You see them there, V, V, variable, variable, variable. However, because they are cross-period efficiencies, the biennial versions have been used to estimate. So in other words, if you look at this one here, it would have been estimating the efficiency of a firm in year T relative to frontier T plus 1, cross period. And therefore, because of that possibility of linear programming infeasibilities, instead of the T plus 1, we use a biennial frontier. So you can see that the technological change biennial has a biennial frontier being used. What about the scale? Now, earlier on, I showed you the scale factor. It was a very long formula, very long, because there were a lot of mixed periods. But now you can see that this scale is using biennial throughout. And so the formula shortens a bit. Okay? It's all relative to biennial and it is in VRS. Okay? So this is a scale change factor. Now we know that the scale change factor reflects the scale effect of period T plus 1 and period T. Okay? How the scale, the size of the firm, is affecting the performance of a firm, or the size of the firm matters to the firm. So this is the scale factor, and finally, this is the Ray and Desli decomposition. So this decomposition is what we call the 3-factor decomposition. Now, what about the Wheelock and Wilson? Remember, this is biennial. Now, this Wheelock and Wilson decomposition was not advanced by the original paper, which is Pastor, Asmald, and Lavelle. They did not talk about this. So we have just brought this into the picture. However, they spoke about something else. They spoke about bulk 2001 decomposition. Okay. it was that one, and we did it last time. That decomposition was looking at also a 4-factor, just like this. But then after they talking about, and I want to write this for your intellectual consumption. After they spoke about efficiency change, and then they spoke about the technological change, they then spoke about the input and output bias, the magnitude index, okay? And then they spoke about the input and output bias. That is what the bulk decomposition, and that was a decomposition Asmaud, Pastor, and Lavelle actually did. Okay, we are not doing that per se, but we are doing a new decomposition based on the Wheelock and Wilson decomposition of 1990. And this decomposition is this. And this is where you got to be taking note, that this decomposition is the one that is similar to the Ray and Desli. Why similar? It is similar because after all, the efficiency change is the same. If I go back to the previous one, you see that is the same. The technological change is also the same as the Ray and Desli. However, here is a difference. The biennial scale efficiency change multiplied by the biennial scale technological change of this Wheelock and Wilson, that is the one that make up the biennial scale change for the Ray and Desli. So the Ray and Desli biennial scale change is equal to this Wheelock and Wilson advanced or extended biennial scale efficiency change times the biennial, scale technological change. So in other words, the Ray and Desli, they combine these two, and the Wheelock and Wilson split these two. And you can see them, especially look at the scale technological change. That one is quite long. Okay, they have 8 elements in that. Okay. But you can also see, as we've already said, you can see that there is a biennial base. Please note that the scale efficiency change has no biennial element. Okay, if you look at it, there's no biennial element because that one is being split directly from the efficiency change. But then the scale technological change, because that one, part of it is being pumped from the biennial technological change. You can see that one, there are biennial elements. In fact, there are quite a number of biennial elements in that. Okay, that one needs to be able to take note of. So this is the Wheelock and Wilson. This is the one, that you use. And coming back to Morrison, are you there? This is the one you are going to be using.
Yes, Doc.
This is what you are going to be using and extend in your undesirable measurements.
Okay, Doc.
This is the one. And you will do the Ray and Desli one as well.
Okay.
McClare, you are there. You will also be doing this too.
Yes, sir. Yeah. Yes, sir.
You also be doing. Eva, are you there? You'll be doing this too. You'll be doing this too. So guys, do not underestimate it. You are going to be using this. And the best way I want you to use them is to do a hypothetical example. And I will do that with you. Once you are able to work and understand it in a hypothetical example, you are good to fly. You can do it in any real data set. So this is a hypothetical example we're about to do. But I'm not going to be able to wrap it up to now. What I'm going to do is I'm going to do that next time, where I will sink ourselves, our mental mind, into applying everything that we have done in the world of biennial.